Hello, I'm Ed Murphy with the Astronomy Department at the University of Virginia, and this is Astronomy 1210, Introduction to the Sky and Solar System, Lecture 17, Ancient Greek Astronomy. Now that we've seen some ancient astronomical monuments from around the world, it's time to study the beginnings of Western astronomy, and that begins with the ancient Greeks. Part of this lecture will be talking about the discovery that the world is round. And so the first learning catalytics question I want you to answer is this: who was the first person to prove that the Earth was round? This is a word cloud, so go into learning catalytics and answer this question. Just type the name of the person who you think was the first person to prove that the Earth was round. Okay. Now that you've had a chance to put your answer in, let's see what the answer is. First, let me tell you what I would have put into this box many years ago is I would have put Christopher Columbus in this box. I was taught when I was in school that one of the accomplishments of Christopher Columbus was that he proved that the world was round. It turns out that that is not true. In fact, it was known in the time of the ancient Greeks that the world was spherical in shape. And in fact, it is known so far back in Greek philosophy that the world is spherical in shape that we don't know who came up with the idea in the first place. The story that Christopher Columbus was the first to prove that the world is round was actually invented by Washington Irving. Washington Irving wrote what we would consider today a largely fictional biography of Christopher Columbus. But that fictional biography became a fixture in U.S. history and the study of Christopher Columbus. And because of those stories that Washington Irving wrote about Christopher Columbus trying to convince the king and the queen that the world was round instead of flat, even though at that time it was well known by all educated peoples that the world was spherical, those stories stuck and became part of history, even though, again, it was not a well-researched, or as we would say today, an academic history. It was much more a piece of fiction. So let's talk about the early cosmological models, the early ideas of what the universe looked like. And these early cosmological models were developed by a variety of ancient Greek philosophers, including Pythagoras, Plato, Eudoxus, and others. And this begins around 550 BCE to about 350 BCE. And starting with Pythagoras, these ancient scientists believed that the universe consisted of a series of concentric spheres that were centered on the unmoving Earth. So at the center of the universe, sitting in the middle, but spherical in shape and unmoving, is the Earth. And surrounding the Earth are a series of spherical spheres. And each of these spheres carries on it one of the planets. So this inner sphere carries the moon. And this sphere carries Mercury and Venus and the Sun and Mars and Jupiter and Saturn. And then finally out here, the sphere of the stars. The motions of the spheres is what creates the motions of the planets as seen from Earth. You'll remember in an earlier lecture, I mentioned that the planets, the Greeks knew of 7 of them: Mercury, Venus, Mars, Jupiter, Saturn, the Sun, and the Moon. The planets were the things that slowly moved through the sky. Now we know today why the planets move through the sky. Mercury, Venus, Mars, Jupiter, and Saturn move through the sky because they're orbiting the Sun. The Moon moves through the sky because it's orbiting the Earth. And the Sun moves through the sky because the Earth is orbiting the Sun. That's what we know. To the ancients, they saw 7 bodies in the sky that wandered through the stars, and they called them planets. And they believed that the motions of these planets were because the spheres were literally turning around. As the spheres turned around the Earth, they carried Mercury or Venus or Mars or the Sun or the Moon across the sky. Even, I should point out, the stars. The stars turned around the Earth on their sphere once every day. Because as the stars turned around the Earth once a day, that caused the stars to move through the sky, to rise in the east and set in the west. Here's another picture of what was going on. We've got the Earth sitting still at the center, and then each of the individual spheres rotating around their own axis at their own speed to create the motion that we see in the sky. And as part of Pythagoras's model, and the one that was developed by other early Greek philosophers, the Earth, the Moon, and the Sun are all spherical or round in shape. And the primary piece of evidence that they lay out for that is the fact that the terminator on the moon, as the moon goes through its shape, through its phases, the terminator is the day-night line right there. The curved terminator when the moon is a crescent and the curved terminator when the moon is a waxing gibbous indicated to the ancient Greeks that the moon had to be spherical in shape. If the moon was spherical in shape, then it was likely that the Earth was spherical in shape. And they got the sphericity or the roundness of the moon just by looking at this terminator line. If the moon was flat, then when the sun was shining on it, you would not get a curved terminator like that. And how much the terminator curved and how that curved changed with position on the moon as the moon went through its phases indicated to them that the moon was spherical. Something that you can easily prove to yourself, as we did the other night when I took that little round styrofoam ball outside and looked at it with a bright light and moved it around. Those shapes can only be explained by a spherical moon. Now, by about 350 BC, Aristotle comes along. Of course, as you know, Aristotle was a student of Plato. He was the tutor of Alexander the Great. Aristotle wrote a number of treatises on physics, astronomy, geography, the natural world around him. And in one of these, Aristotle argues that the Earth is spherical in shape. And so what we're going to do is take a look at some of the arguments that Aristotle used for arguing that the world is spherical. But keep in mind that Aristotle was not the person to prove that the Earth was spherical. It was well known by his day, known for hundreds of years that the Earth was spherical in shape. So what were his arguments that the world was spherical in shape? Well, there are four primary ones that we're going to talk about. I'll come back to this slide here in a minute. But the first one is, as you travel north, the stars near the North Celestial Pole get higher in the sky. You will remember that the altitude of the North Celestial Pole in the sky is equal to your latitude on the surface of the Earth. As you walk closer and closer to the pole, the North Celestial Pole appears higher and higher in the sky. So this picture taken from Hawaii shows the North Celestial Pole fairly close to the horizon because the big island of Hawaii is just a little bit more than 20 degrees north latitude. And so you see there that the pole is about 20 degrees up in the sky. As you go further north, the pole gets higher and higher. Aristotle knew from travels that other people had reported that as you travel south, stars that never rise above the horizon, where he lived at more northern latitudes, become visible. And we've seen this already, that as you travel to the south, new constellations become visible that we can't see here in the north. The Southern Cross being one of those, or Alpha and Beta Centauri, the two brightest stars in the constellation of Centaurus, the Centaur, and Alpha Centauri, you'll remember, is the closest star system to our own. So the fact that as you go to the south, new stars become visible that weren't visible before indicated that you were walking across a spherical Earth. If the world was flat and you looked up in the sky, as you walked back and forth on the flat Earth, the stars wouldn't change in the sky. But if you walk around on a spherical Earth, they do. Another piece of evidence was that as a ship appears on the horizon, it appears from the top down. And that's because of the curved shape of the Earth. When we look at a distant ship, we are looking over a curved Earth. And because we are looking over a curved Earth, the bottom of the ship is not visible, and only the top of the ship is. So here's a wonderful photograph that shows two ships, one that's about 5 nautical miles away, one that's 10 nautical miles away. And you can see for the nearby ship that for the most part you see the whole ship, but for the distant ship over the horizon down there, the bottom of the ship is hidden from view. And this, of course, would only happen on a curved Earth. If the Earth was flat, as a ship sailed away from you, it would get smaller and smaller. But on a curved Earth, what happens is that the bottom of the ship disappears first. So let me show you what's going on there. So proof that the Earth is round here, as in this case, the ship is appearing. So in this case, the ship appears from the top down. And the reason for that is simply if I'm standing over here on a pier looking out over the water, that is my line of sight right there. The ship is hidden from view below the horizon. As the ship comes into view, it will appear from the top down. That is the first thing I will see is the thing that is highest on the ship, and then as it approaches me, I will see things that are lower and lower. So those are a couple pieces of evidence that the Earth is round. His last one that Aristotle laid out was that during a lunar eclipse, the shadow of the Earth is always round, and only a spherical object always produces a round shadow. So we had seen this when we talked about lunar eclipses, this famous photograph by Akira Fuji showing the moon as it passes into the shadow of the Earth and coming out the other side. No matter the conditions of a lunar eclipse, the terminator on the Earth, or I shouldn't say the terminator, I apologize, it's not the terminator, it's the shadow of the Earth right there. The shadow of the Earth is always round. It's always circular. And the only body that always casts a round shadow is a sphere. And in fact, from the size of the Earth's shadow during lunar eclipses, Aristotle and the ancient Greek philosophers knew that the Earth was bigger than the moon, and they knew that the Earth was at least a couple times bigger than the moon, at least 3 times bigger than the moon. We will also see later on that some of the ancient Greek philosophers even knew that the sun was bigger than both the Earth and the moon, and they got that from geometrical arguments. Now, Aristotle had 2 more, I thought, really clever arguments that the world was round. Both of those don't work out today. My favorite one, though, has to do with, of all things, elephants. Aristotle argued that as you go to the west in Morocco, there are elephants. And as you go to the east in India, there are elephants. And he thought that those 2 parts of the world, Morocco in the west and India in the east, must be very close to one another because they both had this exotic animal, the elephant. And of course, what Aristotle didn't know was the difference between African elephants and Asian elephants, the fact that there are 2 main species of elephant. So in fact, they're not that close together. He also presented a theoretical argument that as the Earth and the moon formed and as the Earth formed, material falling towards a center would take on a spherical shape. And that's true because of gravity, but Aristotle didn't really understand gravity. So it was more of a theoretical argument that I think doesn't hold water today because he didn't understand gravity. So that was Aristotle's evidence that the world was round. And here's the thing. He writes this in 350 BC, and he's writing it as if it's well known. And humans never forgot it. We never forgot that the world was round. By the time of Columbus, it was well known that the world was round. The argument in Columbus's day wasn't whether the Earth was round or not. In fact, it was how large the world was, how big the diameter of the Earth was. Because what Columbus was arguing was that he could take small ships and set sail from Spain and make it to the Indies before he ran out of food. The problem is the ancient Greeks had measured how big the world was, and the world was so large that, in fact, if you set sail from Spain, you would run out of supplies, you would run out of food long before you reached the Indies, and you would starve far out at sea. Now, the thing is, it turns out the ancient Greeks' size was right. Columbus was arguing that they were wrong and that the world was smaller than they said it was. For Columbus's sake, then as Columbus set sail, he was lucky then that the New World intervened, because just in fact as they were running out of supplies, they reached the New World, which he didn't know was there. Obviously, had the New World not been there, he and his crew would have perished out at sea. So who was the first person to prove that the world was, to demonstrate the size of the world? The first estimate, good estimate of the size of the Earth comes from an ancient Greek philosopher by the name of Eratosthenes. So he was the first person to determine the size of the Earth, and he did this sometime between 276 and 195 BCE, and so that's right around 200 BCE. What Eratosthenes did is he used the fact that the sun is so far away from us that the rays of sunlight are essentially traveling towards us on parallel lines. And he noted 2 interesting facts. That in Syene, Egypt, which is now Aswan, sunlight fell to the bottom of a deep well, While on the very same day, at the very same time, this is on the summer solstice at noon, on the first day of summer at noon. At the very same day, at the very same time in Alexandria, Egypt, which was about 5,000 stadia north of Syene, he knew that the sun was about 7 degrees away from the zenith. So let's take a look at what happened, or exactly how he did this. So in Syene, he knew that the sun was straight overhead. And he knew that the sun was straight overhead on the summer solstice because deep down at the bottom of the well, the sunlight made it all the way to the bottom of the well. In fact, you can now understand from our study of the seasons in longitude and latitude that this means that Syene must be fairly close to the Tropic of Cancer because on the first day of summer, when the sun is farthest north, the sunlight is straight overhead. But 5,000 stadia away in Alexandria, Egypt, he noticed that the sun was not straight overhead. It made an angle of about 7.2 degrees. So what this indicated to him was not only that the world was round, but it told him how round it was. Because if I'm standing on top of the earth and I see something straight overhead, how far I move across the circumference of the earth will also cause the objects in the sky to shift. To do this, let's do 2 learning catalytics questions. Let's do this one first of all. I'm standing here on top of the earth, and I see the bright star Vega straight over my head. Where does Vega appear to someone on the opposite side of the earth? Someone who started here with me and they walked 180 degrees around the earth to the opposite side of the earth. Where does Vega appear to them? Go out to Learning Catalytics, take a few seconds, answer this question. All right, so where do you think the bright star Vega appears? Well, for me, if Vega is straight overhead, then for the observer on the opposite side of the world from me, it is D, straight below their feet. Now, your answers might be mixed up. Learning Catalytics rearranges the answer. So the right answer here is straight below your feet. It may not have been D for you, but the right answer is straight below their feet. So this person doesn't see Vega because it is straight below their feet. Another way to put it is, for me, the altitude of Vega is 90 degrees. It's 90 degrees up in the sky. For this person down here, they walked 180 degrees around the earth, and Vega shifted in the sky by 180 degrees. Instead of being at an altitude of 90 degrees straight up, it's at an altitude of minus 90 degrees. It's straight down. All right, answer this question. If I see the bright star Vega straight overhead, where does it appear to someone 1/4 of the way around the earth? So go out to Learning Catalytics and answer this one. All right, so for this observer, 1/4 of the way around the earth, where does the bright star Vega appear? Well, if we draw a horizon for this observer right here, their horizon runs up and down, and Vega is right on their horizon. So the answer to this one is C, on their horizon. Another way to get that is, for me standing here, Vega is at my zenith. It is 90 degrees away straight up. If I were to walk 90 degrees across the surface of the earth, Vega would shift down by 90 degrees in the sky. That is, if it's got an altitude, I should say, of 90 degrees right now, when I move 90 degrees, it will shift down 90 degrees and its altitude will be 0 degrees. It will be on my horizon. So this tells me that how far I move on the surface of the earth in terms of a fraction of the circumference of the earth. So here I went 1/4 the circumference of the earth, which is also equivalent to an angle of 90 out of 360 degrees. If I go 1/4 the circumference of the earth, the star will shift 1/4 of a circle in the sky. And what Eratosthenes realized is that if the sun was straight overhead in Syene, Egypt, but in Alexandria, it was 7 degrees away from being straight overhead. That meant that the sun had shifted by 7 degrees of the circle in the sky, which meant that here on the surface of the earth, the distance from Syene to Alexandria was 7 out of 360 parts of the circumference of the earth. Now, How did they get this 7 degrees? Well, they got that from simple geometry. You could take a tall building, you could take a tree, you could take anything that was tall. You look at the shadow length here, and you can use some simple geometry to measure the shadow length and get that at that angle, 7 degrees. But here's what Eratosthenes did. 7 degrees out of a circle of 360 degrees is about 1/50th. So what Eratosthenes said is the distance from Syene to Alexandria is 1/50th the circumference of the Earth, because the sun moved 1/50th of a circle. 7 degrees is 1/50th of a circle. So if 7 degrees is 1/50th of a circle, then the distance between Syene and Alexandria, which is 5,000 stadia, must be 1/50th of the circumference of the Earth. And that means that the circumference of the Earth is 50 times 5,000, or 250,000 stadia. And now, once you know the circumference of the Earth, you'll remember from high school geometry that the circumference is simply 2 pi times the radius. So if you divide the answer by 2 pi, you get the radius. If you divide the circumference by pi, you get the diameter of the Earth, because, of course, the diameter is simply twice the radius of the circle. So this is how Eratosthenes determined the size of the Earth. Now, he sent some runners out, and it was the runners literally counting their number of steps that determined the distance they literally ran from Syene to Alexandria, and that's how they got the distance of 5,000 stadia between the two. All we have to do now to know how close Eratosthenes came is to know how big a stadium was. This stadia is plural, one stadium is the singular. How big a stadium was, if we knew that, then we could figure out how close Eratosthenes was. And here's the problem. There were 3 different values for Greek stadia at the time that Eratosthenes was working, and we don't know which one he was using. But if he was using the common Olympic stadium, then his value was about 20% too large. But if he was using a stadium that was about 1/6 of a kilometer, his figure was within 1% of the correct value of 40,070 kilometers for the circumference of the Earth, meaning that the radius of the Earth is 6,378 kilometers. Now, I think the amazing thing is, regardless of whether he was wrong by 20% or he was right to within 1%, Eratosthenes accurately measured the size of the Earth in the year 200 BCE. Not only did the Greeks know that the Earth was round and spherical, they knew how big the world was, and at worst, they were 20% off, which is not too bad of an error, given how long ago this was. And I think that's really quite remarkable that the Greeks, again, what we saw in our last lecture, they were very clever people. They were every bit as smart as we are. And they were able to figure these things out over 2,000 years ago. And again, humanity never forgot this information. So to put this into practice, I want you to do this learning catalytics question. At 9 p.m. on August 18th of every year, the bright star Vega is nearly straight overhead here in Charlottesville. At the same date and time, the bright star Vega appears 30 degrees from the zenith in Panama City, Panama. How far is it in kilometers from Charlottesville to Panama City, Panama? So think about this again. In Charlottesville, the star is straight overhead. In Panama City, it's not straight overhead. It's 30 degrees away from being straight overhead. I want you to use the method of Eratosthenes to determine the distance across the surface of the Earth from Charlottesville to Panama City, knowing that the circumference of the Earth is 40,000 kilometers. So go ahead, go to Learning Catalytics and answer this question. What is the distance from Charlottesville to Panama City? All right, welcome back. So I wanted you to use the method of Eratosthenes to figure this out. So how do you go about figuring it out? Well, the first thing to realize is that for us, the star is straight overhead. In Panama City, it's about 30 degrees from straight overhead, which means I've moved about 30 degrees across the surface of the Earth. Now, 30 degrees out of a circle of 360 degrees is 1/12 of the circumference of the Earth. So I've walked about 1/12 of the circumference of the Earth. Actually, probably the best way to show this is using my globe right here. So here in Charlottesville, the bright star Vega is straight overhead. In Panama City, it's not straight overhead because this is their zenith. It's 30 degrees away. Because the star is 30 degrees away from being straight overhead, that means I've walked 30 degrees across the surface of the Earth. Well, the full circumference of the Earth is 360 degrees, and I've walked 30 of it, so I've walked 1/12. 30 divided by 360 is 1/12 the circumference of the Earth. If the circumference of the Earth is 40,000 miles, then the distance from Charlottesville to Panama City is 1/12 of 40,000 miles, or 40,000 divided by 12, which is about 3,300 kilometers. So the answer to this one is 3,300 kilometers. All right, that was Eratosthenes, again working around 200 BCE. The next of the great Greek astronomers we're going to talk about is Hipparchus, and I think he's the second greatest of the ancient Greek astronomers. And what's interesting about Hipparchus is there's a disadvantage in the world to being the second best at anything. And that is when the best astronomer in the world comes after you, most people don't think it is worth studying your work, and it ends up getting lost to history. And so what is fascinating about Hipparchus is that even though he was one of the greatest Greek astronomers, only one of his original writings survives. Everything we know about Hipparchus comes from other astronomers who wrote about the work that Hipparchus did, especially an astronomer by the name of Claudius Ptolemaeus, who we'll see here in a minute. Now, we don't even know the dates for when Hipparchus worked. Based on lots of lines of reasoning, we think he carried out his work between about 160 BCE and about 127 BCE on the island of Rhodes in the Mediterranean. So roughly about 150 BCE was when Hipparchus was working. Now, of course, all of this was done pre-telescope. There were no telescopes at this time. So Hipparchus was using observations of the sky using devices like this for measuring angles in the sky. So what did he do? He built an observatory on the island of Rhodes, and he built instruments to measure the sky. And amongst many other discoveries that Hipparchus made was he invented the magnitude system. And it's worth mentioning the magnitude system because astronomers still use it today, over 2,000 years later. It's how we measure the brightnesses of stars. So the apparent brightness of a star, and what I mean by apparent brightness is how bright it appears in the sky, depends on two things. And it depends on the luminosity of the star, how bright the star is intrinsically, that is how much energy it's giving off every second. And it also depends on the distance from Earth. A star in our night sky can be bright because it's either close to us or because it's giving off a lot of energy every second. And in fact, for most of the stars, especially the bright ones that you can see with the naked eye, it turns out both of those are true. It turns out they are the brightest stars in our night sky, both because they're close to us and because most of them are very luminous stars, giving off a lot more light every second than our sun does. And the brightness of a star in our sky is measured in a unit called apparent magnitudes. So around 150 BCE, Hipparchus compiles a catalog of about 850 stars. He measures their position in the sky. He measures their east-west position along the ecliptic. He measures their north-south position using the height above the ecliptic. He lists the brightness of the stars. And the brightest stars he called the first magnitude stars. And the second brightest stars he called second magnitude stars. And the third brightest stars were third magnitude stars, and on down until the sixth magnitude stars were the faintest ones he could see. Now, at first, this system seems to make a lot of sense. The brightest ones are first magnitude, the next brightest ones are second and third and fourth, all the way down to sixth magnitude stars. Unfortunately, it turns out that many of the objects in the sky are actually brighter than first magnitude. Hipparchus didn't have a way to accurately measure how much light these things we were receiving here on Earth from these things. And once we invented telescopes and we had ways to accurately measure how much light we were receiving, it was pretty clear that there were stars that were brighter than the first magnitude. Well, what do you do in that case? If stars of the first magnitude are the brightest stars, and there's some things that are brighter than that, you need numbers that are less than 1. And so that means that we today have stars of the 0th magnitude. We even have stars of the negative first magnitude. Sirius, which is the brightest star in our night sky, has an apparent magnitude of minus 1.5. And this is why the magnitude system gets a bit confusing. There are two things confusing about it. The first one is that the numbers run backwards. A sixth magnitude star, which is the faintest star that you can see with the naked eye, a sixth magnitude star is dimmer than a second magnitude star. All right, so let's look at some things. Here's the magnitude scale. So let's start again with Hipparchus here. The first magnitude stars were the brightest stars. Polaris is about magnitude, second magnitude star up there in the sky. The faintest things you can see with the naked eye are about sixth magnitude. With binoculars, you can see 10th magnitude, and the faintest things you can see in big telescopes are in the high 20s. The Hubble Space Telescope can see things that are about 29th magnitude. That's how faint it can see. Now, brighter than the first magnitude, we have Sirius, which is magnitude minus 1.5 in the sky. Jupiter at its brightest and Mars at its brightest, they're both about magnitude minus 2.5, and Venus at its brightest is about magnitude minus 4. The full moon is about magnitude minus 13.5, and the sun is magnitude minus 26. Now, what's fascinating is Hipparchus invents this magnitude system, and we still use it today. I don't know if you looked very carefully at the star charts that I told you about in the very first lecture, these ones from skymaps.com, but all star charts do this. You'll notice that the brightness of the stars is represented by the size of the dot, right? Arcturus is a very bright star, it's a big dot. Vega is a very bright star, it's a big dot. There are lots of little faint stars in the sky, and those are represented by tiny dots. Well, down here in the lower right-hand corner, there's actually a little key that tells us about these magnitudes. And if we blow that up so that we can see it, there we go. There are the star magnitudes. Stars of that size are minus first magnitude, and those are 0th magnitude stars, first, second, third, fourth magnitude stars. So let's put all this to the test. Here's a learning catalytics question. There are 3 stars in our night sky, and they have apparent magnitudes of 5.6, 6.9, and 9.8. In learning catalytics, I want you to rank the brightnesses of these stars. I believe the way I've worded it in learning catalytics is rank them. Rank the 3 stars in terms of brightness. So go ahead, go to learning catalytics, answer that question right now. Rank the 3 stars, 5.6, 6.9, and magnitude 9.8. Okay, welcome back. So what did you come up with? Well, here's the thing about the magnitude system. You always have to remember that fainter objects have higher, larger apparent magnitudes, and brighter objects have smaller apparent magnitudes, right? That is, of these stars, the brightest of these stars is the magnitude 5.6 star. And the dimmest of these stars is the magnitude 9.8 star, and the 6.9 is in between. So the hard thing to remember about the magnitude system is the smaller the number, the brighter the star. And I think it's amazing that Hipparchus invents this system 150 BCE, and we're still using it today with the Hubble Space Telescope in the 21st century. The other thing that Hipparchus did was he compiled a star catalog. I've already mentioned the star catalog of 850 entries where he measured the positions of the stars in the sky. And he compares his star catalog to a star catalog that's about 160 years old. And what he found was that the north celestial pole had shifted in the sky. All the stars in the sky had shifted over from that catalog that was made about 160 years earlier. And I think this is really quite amazing, because if I measured the brightnesses, not the brightnesses, but the positions of the star today, and I compared them to a catalog that was 160 years old and saw that everything was different, I might just chalk it up to the fact that the people who did the catalog long ago had made a mistake. But he knew they were better than that. He knew that they didn't make a mistake. He knew that the whole sky has shifted. And this shift is caused by precession. We saw this earlier in the class, the fact that the Earth is not only spinning, but it wobbles. And it wobbles every 26,000 years. And Hipparchus was the first person to discover precession around 150 BCE. So to show you an effective precession, I want you to do this. So this one's going to take you a little while, but it's worth pausing the video here once I'm done explaining this, and then going off and doing this and coming back. Everybody's familiar with the fact that they have an astrological sign. So for example, my birthday is December 16th, and I'm told that my astrological sign is Sagittarius. If you don't know what yours is, just look it up on the internet, type astrological sign. You'll find astrology out there. You'll find the dates listed. So determine your astrological sign. Your astrological sign is called your sun sign. It is where the sun is on the day you were born. So now I want you to go into Stellarium, and I want you to set Stellarium for your day and time of birth, or just your day of birth is enough. Sorry, you don't have to set the time, just the day of birth. And then go to about noontime on the day of your birthday so that the sun is above the horizon and you can see it. So even if you were born at 2 o'clock in the morning, go ahead and set it for about noon on the day you were born so that you can see where the sun was in the sky. And then down there at the bottom of Stellarium, actually, let me go ahead and bring this up and I can show you exactly what I'm talking about. Let me do it for me here. Just giving Stellarium a second here to load. All right, so let me bring Stellarium over here so you can see what I'm talking about. All right, so there's Stellarium. So the first thing I want to do is type in my birthday. So I'm going to bring up the date and time window here, and I'm going to bring up my birthday. And so it's December 16th. Oops, 16th, 1966. It'd just be faster to type it at this point. Oops. That's not right. Okay, there we go. December the 16th, 1966. Okay, so I've typed my date and time of birth in there, and now I'm going to go to noon, just so that the sun is up there nice and high in the sky. So there we go. It'll go to noon right there. Just put the sun. Doesn't have to be exactly noon. So there's the sun up there in the sky. Your astrological sign is your sun sign. It's supposed to be the constellation that the sun is in on the day you were born. So let's go down here and actually let's see what constellation it's in. So the first thing I'm going to do is there's a whole series of buttons down here in the lower left-hand corner that allow you to bring up the constellations. So the first thing I'm going to do is bring up the labels of the constellations. And the second thing I'm going to do is bring up the art of the constellations. And then I'm even going to bring up, you can go over here to the setting windows, the sky and viewing option windows over here. And let's see, where is it? Oh, actually, you know what? I think it's under the configuration window. Nope. Actually, it is over here. It's with the markings. So over here with the star lore, sorry, that's what I'm looking for. With the star lore, I am going to add some buttons here so you can do show asterism lines, show the constellation lines, show the constellation boundaries. And that's what I'm going to do right now is I'm going to show the constellation boundaries right there. So what I've done is I've put the boundaries of the constellations up there and I've put the names up there. And now I'm going to zoom out a little bit. And what I see is on the day I was born, I'm told that I'm Sagittarius. But here's the constellation of Sagittarius right here. And you'll notice that the sun is not in Sagittarius. On the day that I'm born, December 16th, the sun is actually in the constellation of Ophiuchus, the doctor. I've actually waited my whole life for somebody to come up to me and say, what's your sign? So that I can say, why, it's Ophiuchus. And they'll say, well, Ophiuchus, I don't even know what that is. It's not one of the traditional astrological signs. You might remember when we were talking about the sun moving through the ecliptic way back in lecture 1, I guess it was. We talked about the fact that there are 12 traditional zodiacal constellations, and then there's an extra, Ophiuchus. And for a few days in December, mid-December of every year, the sun actually passes through the leg of Ophiuchus. So why is my sun sign Sagittarius if the sun is in Ophiuchus? And the answer to this is that astrology was invented about 2,500 years ago. And when astrology was invented, on my birthday, the sun was in Sagittarius. The reason that it has shifted out of Sagittarius is because of the precession that Hipparchus discovered. So to show you this, let's go down to my date and time. Let's imagine, in fact, that I was born about minus 500 BC. Or sorry, about minus 5, not 5001, about minus 500. In the year minus 500, which is about 500 BCE, the sun was in Sagittarius. It was in my sun sign. So I want you to do this. I want you inside Learning Catalytics. Well, first of all, bring up Stellarium, type in your birthday, see where the sun is today, and then see where the sun was 500 years ago. And I want you to compare where your sun is today on your birthday to your astrological sign. And what do you find out? Do you find that the sun is in your astrological sign? Is it shifted one constellation over, two constellations over, or was the sun shifted into a constellation that's not one of the astrological sun signs? So in my case, it was shifted into something that was not one of the astrological sun signs. You might get well, in fact, depending on the time of the year you're born, it could be any one of these answers. So go ahead and do that real quick. Okay, so what did you find? What you probably found is that the sun was shifted either one or two constellations over. In some cases, the constellation is so big that, in fact, it's correct on both. If I remember correctly, I think it's Virgo. Sometimes people can see that their sun sign is Virgo and that the sun is actually in Virgo today. What most people find, though, is that the sun is shifted one constellation over. It's shifted one constellation to the west of the constellation that it's supposed to be. So in my case, instead of being Sagittarius, it was one constellation to the west of that, over there in Ophiuchus. In some cases where the constellation is really small, it can actually be shifted two constellations over. Or if you're lucky like me and you were born in mid-December, it's actually shifted into Ophiuchus, which is not even one of the astrological sun signs. So what Hipparchus discovered, although he didn't really understand what he had discovered, was he discovered the wobble of the Earth, the fact that the Earth is precessing, it is wobbling every 26,000 years. And what we saw a few lectures ago is that this precession, or this wobble, causes the position of the pole to change in the sky. Polaris is the pole star today, but it wasn't always the pole star. And it won't always be the pole star. Thuban was the pole star about 5,000 years ago, about the time the pyramids were built. And Vega will be the pole star about 12,000 years from now, in the year 14,000 CE. Hipparchus discovered a few other things. He found that the distance to the moon is about 59 times the Earth's radius. The actual value is 60. Look at what I just said there. We're talking about a man that lived 200 BCE, and he knew accurately the distance to the moon. Not only did we know that the Earth was spherical, not only did we know the size of the Earth, we even knew the distance to the moon in 200 BCE. He was able to determine the length of the year to within 6 minutes, and he actually looked for the parallax of the stars. Hipparchus was one of those ancient Greek astronomers that believed that the Earth was the center of the universe, that everything went around the Earth. And one of the reasons they believed that was not out of ignorance, but actually out of making a direct observation of the sky. And that observation was, if the Earth was really going around the sun, as the Earth goes around the sun, the nearby stars should shift back and forth, not because the stars are moving, but because we're seeing them from two different perspectives. If you hold your finger out at arm's length and look at your finger with your right eye, and then your left eye, and then your right eye, and then your left eye, as you blink your eyes back and forth and you see your finger from two different perspectives, your finger appears to move back and forth. Hipparchus realized the same thing is true for the stars and the planets. As the Earth goes around the sun, when we look at the stars and the planets, they should appear to shift back and forth in the sky. And again, not because they're shifting, but because the Earth is on one side of the sun, and then 6 months later, the Earth is on the other side of the sun. And as we see them from different perspectives, they should move. Well, he carried out this observation. He looked in the sky to see the stars shifting back and forth, and he didn't detect any shift at all. And Hipparchus believed because of that the Earth could not be orbiting the sun. It must be that the Earth was sitting still at the center of the universe and everything was going around the Earth. The problem that Hipparchus ran into that he didn't understand is that the stars are so incredibly far away, that their parallax shift is so small that it takes a large telescope to detect it. He had no hope of seeing that parallax shift with his naked eye and with the crude instruments that he had. And they understood that one solution to this was that the stars were so far away that the parallax shift was too small to measure. But that universe would have been so phenomenally big that they decided that that couldn't be the case. It must be that the Earth wasn't moving. And they came to exactly the wrong answer there. In fact, the universe is far, far vaster than they believed. And the stars are so far away that we can't see their shifting with our eyes. Well, the last of the great Greek astronomers that I'm going to talk about is Claudius Ptolemaeus. Ptolemy lived around 140 CE, so about 300 years after Hipparchus. And much of what we know about Hipparchus actually comes from Ptolemy. Ptolemy wrote in his Almagest, we'll see that here in a second. He wrote a lot about Hipparchus in there, and a lot of what we know about Hipparchus comes from Ptolemy's writings. So he compiled a series, a 13-volume series that we know today is the Almagest, and it comes from the Arabic words Al-Majisti, which is Arabic for the greatest. It is our main source of information about Greek astronomy. Now, we don't know what Ptolemy looked like. Here's a potential drawing of what he looked like. Here is a Latin translation of the Almagest. This is actually a star chart, a table of the positions of the stars. So these are the names of the stars over here. And you will notice that in these times, in the Greek times, in Ptolemy's time, for the most part, the stars did not have proper names. They were described by their location in the constellation. And then this was their longitude in the sky along the ecliptic. This was their latitude in the sky, how far north or south of the ecliptic they were. And then this one right here, I love this column right here, that is their magnitude in the sky. So some of these stars here are in Orion. So let's look at this one right here, this particular first magnitude right here. It is the Lucida, K est in pede sinestro, est in, sorry, it's a little small. I'm having a hard time reading it, but I know it by heart. It's Lucida, which is the bright one that's in the left foot. It's in common with the water. That is the bright star Rigel, which forms the left knee, the left foot of Orion the Hunter. But in ancient times, it was also considered to be a part of the constellation of Eridanus the River, which is why he says est commune, it's in communion, it's in the water as well, or it's a part of the water as well. Okay, so Ptolemy was able to use parallax to accurately determine the distance to the moon. So he got it even better than Hipparchus did. He got it within 3%. And he was actually able to use parallax to do this. He realized that as the Earth spins, when we're on one side of the Earth and we look at the moon, we see it against one background. And 12 hours later, when we look at the moon, we see it against a different background. But it's a really complicated measurement to make because the moon is also moving around the Earth. So what he had to do was calculate how much the moon moves around the Earth and subtract that, and then measure the moon in the morning when the moon was rising and when the moon was setting. And from that, he was able to accurately triangulate the distance to the moon to within 3%. Ptolemy also developed a model to explain the motions of the planets in the sky, a geocentric model with the Earth at the center of the universe. And this geocentric model was so successful in predicting the positions of the planets that it survives for 1,300 years. Imagine inventing something that people use for 1,300 years. Ptolemy also, in this star atlas here, laid out 48 northern constellations. And these 48 northern constellations were the basis for the International Astronomical Union's definition of the 88 constellations in the sky in 1928. The constellations that we still use today were the ones that were laid out by Ptolemy. Of course, he didn't invent them, but he wrote them down in his star catalog. So let's go back to this geocentric model here for a second that Ptolemy came up with. What motions did Ptolemy have to come up with? Ptolemy needed to account for all of these motions. First of all, he needed to account for the fact that the sun, the moon, the planets, and the stars, they rise in the east and they set in the west every day. Now, you and I would say that's because the Earth is rotating, but Ptolemy believed the Earth was sitting still. So he had to have spheres moving in the sky that carried the sun, the moon, the planets, and the stars. And they carried the stars, the moon, the planets, the sun from east to west every day. He also had to account for the fact that the sun moves from west to east through the stars every year at an irregular rate of about 1 degree per day. Now, you and I would say this is because the Earth is going around the sun. And as the Earth goes 360 degrees around the sun in 365 days, the sun moves about 1 degree per day. But it doesn't move at a nice uniform regular rate, and that's because sometimes the Earth is closer to the sun, moving a bit faster. Sometimes the Earth is farther from the sun, moving a bit slower. So Ptolemy had to explain that the sun is moving through the stars at about 1 degree per day, but it's an irregular rate. And he had to do it not because the Earth is going around the sun, because of course he had the Earth sitting still at the center. He had to use it explaining the sun. The moon does the same thing. The moon moves from west to east through the stars every month at an irregular rate of about 12 degrees per day. The sun goes around the Earth 360 degrees in about 30 days, which means that it moves about 12 degrees per day. He had to explain the motion of the moon. You and I would say that the moon is orbiting the Earth. Ptolemy, on the other hand, believed the moon was mounted on a sphere, and that sphere was turning at an irregular rate of 12 degrees per day. Here's the hardest one to explain. The planets move from west to east through the stars at varying rates. For example, Saturn takes about 30 years to go all the way around the sky. Jupiter takes a little bit less than 12 years to go around the sky. But here's the hard part. At times, they stop going from west to east. They move backwards and go east to west for a while, and then stop and go back to moving west to east. Now, it's worth explaining here what's actually going on, and then later on we'll see what Ptolemy believes is going on. So here's what's actually going on. We call this retrograde motion. If you watch the planets very, very carefully, you're going to see that they move through the sky night to night from west to east, and that's just their orbital motion around the sun. But once a year, a planet will stop, move backwards for a while, stop, and then start moving forward again. And we call this retrograde motion. And here's what it looks like. The planet is moving through the sky. It stops. It moves backwards for a while. It stops. And then it starts moving forward again. And you might ask, why does it do this crazy motion like that? Well, we know today why it is. And there's a very simple explanation behind it. And it has to do with the fact that the Earth is orbiting the sun faster than the planet, and it appears to move backwards when we're passing the planet. Here's an example. Imagine that you're driving on the interstate at 70 miles an hour, and there is a car in front of you that's traveling 60 miles an hour. As you go past that car, you're going 70, it's going 60. As you go past that car, it looks like that car is moving backwards. Now, the car is not actually moving backwards. It only looks like it's moving backwards to you because you're going faster than it. You're going 70. You know that it's going forward at 60, but as you pass it, it looks like it's going backwards. As we pass the outer planets, as we orbit the sun faster than they do, when we pass them, it looks to us for a little while like they're going backwards. And we call this retrograde motion. And Ptolemy had to explain this in a case where the Earth was sitting still and the objects were orbiting around the Earth. He also had to explain why the paths of the moon and the planets are tilted with respect to the sun in the sky. We know this today because all the planets, although they all orbit the sun in the same plane, each planet has its own inclination, its own tilt with respect to the Earth's orbit around the sun. All the planets are not precisely in the same tilted orbit that the Earth is. They all have their own little tilts. And so he had to explain that. And then he also had to explain an interesting fact that Mercury and Venus always appear close to the sun in the sky. You never see Mercury and Venus in the middle of the night. You only ever see them in the early evening or the early morning when they're close to the sun in the sky. All right. So how did Ptolemy explain all these observations, all these motions in the sky? He did it using a really clever system. He had a system where the planets are orbiting around the Earth on a circle called the deferent. But the planet itself is not on this giant deferent, on this giant circle. The planet itself is on a smaller circle called an epicycle, E-P-I-C-Y-C-L-E, an epicycle. And so as the deferent, so let me go back again. The planet is on the epicycle. The center of the epicycle is orbiting the Earth on the deferent. Now, in the case of Jupiter, it takes the planet 12 years, a little less than 12 years, to go all the way around the deferent and come back again. And once every Earth year, the planet orbits around the epicycle like this. So for part of the year, when the planet is on this part of its epicycle right here, although it's moving forward on the deferent, it's moving backwards on the epicycle. And because the epicyclic motion is faster, that dominates, and the planet appears to be moving backwards for a little while. Most of the time when the planet is here or here or here, it seems to be moving forward through the sky as the epicycle gets carried forward. But like I said, once a year, because it goes around this epicycle once a year on the inside of the epicycle here, it's traveling so fast backwards that for a while from the Earth, it looks like the planet is moving backwards in the sky. Now, Ptolemy did these calculations, but it turns out he had to make some changes. In order to explain the motions of the sun and the moon and the planets, the Earth, it turns out, couldn't be at the center of the deferent. It had to be offset a little bit. And so he called this the center of the eccentric, but the Earth was placed off on one side. On the other side, we get a point called the equant point. And as the planet orbits around the deferent right here, with a period that depends on the planet. As I said, with Jupiter, it takes a little less than 12 years to go all the way around. It orbits not the Earth at a constant rate, but it orbits the equant at a constant rate. And what that means for the Earth is that we see it move in an irregular rate around the deferent. Right? If we were at the center of its motion and it went at a uniform rate around that center, it would go evenly through the sky. But because we're off on one side, sometimes it's closer to us and it appears to move faster, and sometimes it's further away and it moves slower. This was a really complicated mathematical model, but here's the most amazing thing about it. It was so accurate at predicting the positions of the planets that it survives for 1,300 years. For 1,300 years, astronomers don't feel the need to significantly improve on Ptolemy's model. So real quick about Ptolemy's model, during retrograde motion, you answer this in learning catalytics. During retrograde motion, according to the Ptolemaic model, a planet is A, at varying distances from the Earth, sometimes closer, sometimes farther. B, closer than average. C, farther away from Earth than average, or D, always at the same distance from Earth, since the planet orbits the Earth in a circle. So this is, what I'm talking about here is specifically the moment when the planet is going through retrograde motion. When the planet is moving retrograde, which one of those statements is true? So go ahead and go out to Learning Catalytics for a few minutes and answer that question. All right, welcome back. So what's the answer to that one? The answer to that one is when the planet is going through retrograde motion, it only, as it moves in its epicycle like this, it's only moving backwards as seen from the Earth when it's on the inside of the circle here. So the best answer to this one is a planet is B, closer to Earth than average. That is when it's going through its retrograde motion. When the planet is going retrograde, the planet is on the inside of its circle. And here's something that made sense to Ptolemy. The planet is on the inside of its circle, which means it's closer to Earth than at other times, which means it should appear brighter in the sky. And sure enough, today, when we pass these planets, it turns out when we pass the planet, it's also closest to us in the sky, and it appears brightest in the sky. So this all made sense to Ptolemy. And this model was so good, as I said, it persisted for 1,300 years. In our next lecture, we're going to see the next major development in astronomy, which doesn't happen for 1,300 years after Ptolemy. And that is with Copernicus inventing a model of the solar system where the sun is at the center instead of the Earth. So join me in the next lecture when we're going to learn all about Copernicus and the early Renaissance astronomers.